So it was during my PhD, together with Professor Erik Smolders and Professor Dirk de Vos, that we started developing a new fertilizer with the goal of proposing a new way to link the recycling of phosphorus from liquid bio-waste streams to the reuse of that phosphorus in the form of a slow-release fertilizer. And the fertilizer that we worked on was based on a specific type of material, a layered double hydroxide, or in short, an LDH. An LDH is a layered material that consists of charged metal hydroxide layers, and these layers have a positive charge. And because of that positive charge, they also attract negatively charged anions. And these anions settle in between those layers, so you get kind of a lasagna-like material. And the anions that are bound in such a material can be carbonates, it can be chloride, but also they can be plant nutrients, such as phosphorus in the form of phosphate. Now, how can such a material act as a fertilizer? Well, we saw that if we apply such a fertilizer to a pH neutral or to an alkaline soil, then the phosphate can be released from such a material via anion exchange with soil solution anions. So carbonate or sulfate that we find in soil solution, they exchange phosphate in that material, and upon that also the phosphate is released and can be taken up by plants. In acid soils, there could also take place another mechanism, namely that in acid conditions, such an LDH is rather unstable. So it is a hydroxide material, and in acid conditions of an acid soil, the layered material will start to dissolve, and thereby it will start to release the phosphate that is bound, but also it will release the metal cations that you find in these layers, which can be, for example, magnesium or zinc. And also those can, next to the phosphate, have an effect on plant nutrition. And the first one is that these LDHs, they are quite selective towards certain anions. And it has also been found that LDHs are quite selective towards phosphate. And therefore, research has shown that these LDH materials can be used as adsorbents for phosphorus in wastewater. And therefore, we are addressing a sustainable source of phosphorus, and we obtain phosphorus-loaded LDH materials. And my research has shown that these phosphorus-loaded LDHs can also be used as a phosphorus source for plants. Another interesting thing about these fertilizers is related to the properties of LDH fertilizers. Namely, they are slow-release fertilizers. And that is, for example, in comparison with the conventional phosphorus fertilizers, such as triple superphosphate or monoammonium phosphate. These are very soluble sources of phosphorus. So when you apply them to a soil, they release their phosphorus almost instantaneously. That is not the case with these phosphorus LDH fertilizers. And the interesting thing here is also that we can try to match the rate at which these nutrients are released with the rate at which also plants are taking up the phosphorus. And that in certain soil systems, I think, can have a positive effect on the phosphorus use efficiency of the fertilizer, of the phosphorus fertilizer application. And then lastly, also the slow release effect of this fertilizer can have an environmental benefit, because the fertilizer is not exposing all of its phosphorus at once to the environment. And that means that also that phosphorus is better protected against, for example, leaching of phosphorus in the soil or runoff. And therefore, I think that slow release fertilizers and, for example, also recycled slow release fertilizers can be an important tool to protect the environment. Making phosphorus fertilizer application more sustainable is probably one of the biggest challenges for plant nutrition in the upcoming decades. But I think there are two very important aspects to that. And the first one is that we need to look at the source of our phosphorus fertilizer. So a lot of the phosphorus fertilizers these days are derived from rock phosphate, which is a non-renewable source of phosphorus. But next to that, we also find quite a bit of phosphorus in residues and in waste streams. And I think we need to reuse and recycle as much as possible of that phosphorus, considering all the streams of interest, such as crop residues, manure, animal byproducts, such as bone ash, and also the phosphorus that we find in sewage wastewater. And for the phosphorus in sewage wastewater, I think there is already quite a bit of interesting technology available to recycle that phosphorus, such as sludge ash technology or struvite precipitation, and possibly also the LDH absorption technology and the LDH fertilizers can be a coexisting technology here. So overall, indeed, capture as much of the phosphorus as possible from the waste streams, and also do it in such a way that we can recycle that phosphorus back into agriculture. And secondly, the second important aspect here is, I think, that we need to consider the efficiency of the phosphorus fertilizer application itself. So how much of the phosphorus that we apply is in the end also taken up by the crops. That is also what we want to maximize. But well, in order to maximize that, I think that the approach to do that can be very different for different regions, and also very different for different crop production systems. So in Belgium, for example, where I'm from, here there has already been a lot of nutrient input in the past decades, also because of high livestock density. So the goal here would really be to recycle as much of the phosphorus and also make use of the phosphorus that has been building up in our soils over the years, which we call the legacy P. But the approach can be, for example, be very different in regions that are still very dependent on the input of mineral phosphorus fertilizers, for example, in sub-Saharan Africa. So here I would say that the approach would rather be to use the available mineral phosphorus fertilizers as efficiently as possible, and to develop smart integrated techniques that would make the best of the phosphorus fertilizer input. At the moment, I'm still exploring the capabilities of slow release fertilizer compounds, but not focusing as much anymore on phosphorus, but more on micronutrients. But the main objective of my research is still focusing on improving the nutrient use efficiency of fertilizers application via fertilizer development, trying to limit the losses of nutrients to the environment and to look for opportunities for nutrient recycling. And for example, I am working on a project of recycling a boron waste stream and doing it in such a way that we obtain a slow release boron form. And that is a project that I'm doing together with Dr. Jakob Sandner from the Bogo University in Vienna. And slow release of boron can be very interesting too, because boron is a nutrient that leaches quite easily in the soil, and therefore it can also get lost for plant uptake. And next to that, I'm working quite a bit on the development of new molybdenum fertilizers. So molybdenum is an essential micronutrient that so far has not yet received a lot of attention in terms of new fertilizers. And that's something that I'm working on together with Professor Mike McLaughlin. And also from January onward, I will join his research group in Australia to work on this topic. And lastly, also I am involved with some PhD projects in fertilizer field studies in Africa, for example, where we are looking at phosphorus application in upland rice systems in Madagascar. And also in the future, I am hoping to be more involved in field trials in sub-Saharan Africa.